Hi all. In this video, I'm going to talk about designing steel columns under combined actions. It means we have both compression and bending moment in the column, which is a real case. So most of the time, because the column is supporting the beams transfer some shear and bending moment to the column. So we need to consider that bending moment, which decreases the capacity of the column for carrying the compression and axial loads. So here for the recap, as we discussed before, we talked about how to design the columns based on CSOC guideline, and it is also based on New Zealand standard NZS 3404, designing the steel structures. So here you can follow the flow chart to be able to design the column for the axial compression force only. So to do so, the first step is to find the section capacity phi and S from the table. So in that table, you can easily choose your cross section and read the capacity for that specific cross section. Then you need to find the effective length for your column, which depends on the restraints and supports of your column, which we need to find KE from the table that we discussed. I can find it here. So for the effective length, we have LE equals to KEL. So KE, depending on the restraints that you have, can vary between 0.7 to 2.2. So you find out about your supports, then you can find KE and multiply it by the length. Please note that it is always not the same in both directions. Sometimes in X direction, you have different supports from the Y direction. So you will need to do this for X and Y directions separately, because also as we know, the chance of buckling in the Y direction is higher, and load carrying capacity because of that buckling is lower in Y direction as well. So after defining the effective length, we can find the slenderness reduction factor from a table. Again, from CSOC guideline, you can see in Appendix B, there are some tables, the same cross-section that you use here. You can read the slenderness reduction factor, which depends on the effective length from that table. And after that, you will be able to calculate the member compression capacity. So as you can see, we have section capacity and member capacity. So there are two different things, and you need to calculate both and compare it with the load that you're applying to your structure. So for the member compression capacity, as you can see, we calculate for X direction as well as Y direction because of the same reason that I said. In Y direction, there is a higher chance of buckling, so you need to calculate for X and Y separately and see which one is less. So you calculate both of them, and the minimum value between these two gives you the phi and c that you need to compare it with n star, which is your design axial force. So as you can see, we have two checks. One, your design load must be less than section capacity, and your design load must be less than the member capacity. So this flowchart shows the design for column under compression force only. Now we want to see what if we have bending moment as well as compression force. So there are different cases. Sometimes you have compression as well as bending moment about minor axis, or you have axial force as well as bending moment around a major axis. And sometimes you have bending moment about both of them. But in this paper or in this course, we just focus on simple combined action check, which means that we only have bending moment about x-axis, which is our major axis, and also we have compressive force. So our major axis bending only, we call it mx star, and also we have axial compression n star. So these two are design forces, and after design analyzing your structure, you will find out about your mx star and n star from the analysis, and now you take them and see what member is suitable for carrying those loads. Okay, so now you can see that we have step one, which is finding section axial compression capacity. So again, as I said, we have section capacity and member capacity. So it's the same thing that you find it from the table from CSOC Appendix B. So here is the table for I section, which is universal column. And if you have other sections, you can find the suitable table and read the numbers from that table. So we choose our member. For example, we have 200 UC 59.5, and we can read phi NS, which is the section axial compression capacity, which is 2057. And you compare it with your axial force, design axial force. And if the axial force that you are applying on the member is less than your capacity, that's okay, which should be. The next step is to find the effective length based on the restraints that you have. And as I said, for X and Y may be different, and you need to calculate for both. So if I want to draw here, if we have a frame like this, for this column, if you consider this column, because the top part allows to move, so it can move. As you can see, it is similar to this case because you have fixed end and the other part allows to move. So the movement is free. It can be also this case, it depends on your assumptions. Sometimes we consider that the floor is a rigid floor, but it is in a case that you have a rigid floor here, but if you have a truss here, it is not a rigid floor. So when it moves, it will be like a free and one. So we will consider 2.2 for this case. And for the other case, because one end can move and the other end cannot move, so we can consider this case, because if you don't consider, you want to consider two like this, you will fix the horizontal movement. So you can consider this case for the other column. As you can see, these two are the highest numbers in the table. So if you are not sure if you, for this case, you want to use this one or this one, it is safer to choose the higher number and it is safer. So it is better to use the higher number in case you are not sure which one would be more suitable. Okay. Next step, as we discussed in the compression design, we need to find the slenderness reduction factor. So from the same table, when you choose your member, you can read the alpha C. As you can see, we have two tables, one alpha C for x-axis, the other one is alpha C for y-axis. So they are different from each other, and you need to choose the correct value to calculate your alpha 6 and alpha cy. Now we can calculate the member axial compression capacity. So we have phi n cx and phi n cy, which is calculated by alpha 6 times phi ns or alpha cy times phi ns. And the minimum of these two values will be compared to your design axial force. And if the design axial force is less than capacity, that is okay. Otherwise, you have to change the member and repeat the process before continuing the procedure. Next step, we want to see if we need to check the combined action requirement or not. So if the axial force that the axial design force you're applying on the column divided by the capacity, which is phi nc, is more than 5%, you need to consider the combined action check, which we will talk about in the following slides. But if n star over phi nc less than 5%, it means you don't need to continue, and the column or the cross section that you chose for the column is suitable and you don't need to check further. So we want to see what if that ratio is higher than 5%. Now we need to find the bending moment capacity of the member. So for this, we have Appendix A of CSAT document, and you can find the number, for example, for 200 USD 59.5, the phi m SX is 177. So as we discussed, we said in this case, we just consider the bending moment around x-axis. So you only need to find phi m as x, which is around x-axis. You don't need to be worried about capacity in y-axis because we are not considering any bending moment around y-axis. So in this case, I said this is the bending section capacity. So we have section capacity as well as bending member capacity, which is phi m bx. There are a lot of calculation involved in phi m bx that we don't want to talk about. We just want to ignore that, and we consider that bending moment capacity equals to section moment capacity to simplify this part. So after this, you need to calculate the reduced bending moment capacity of the member, which is phi m ox, which equals to phi m bx times 1 minus ns over phi nc. So if mx star, which is your bending design moment, is less than capacity, so the member that you chose is okay. Otherwise, you have to choose another member and repeat the whole process. That's it for designing the columns. If you want to have a look at the example, you can refer to CSAC guideline to read the example as well. Hope it was useful, and see you soon.